Now in Lesson 4.3, we dealt with compound probabilities that were using OR. And so when we see the word OR, that always means to add the separate probabilities. In Section 4.4, we're going to discuss the multiplication rule of probability. And one trigger to let you know that you need to multiply is the compound word used is the word AND. So AND means multiply, OR means add. The multiplication rule is used for finding P of A and B, or the probability that A and B occurs. This is the probability that event A occurs in the first trial and event B occurs in the second trial. Now if A and B are independent events, meaning that B is not affected by the outcome of A, then the probability of A and B is equal to the probability of A multiplied by the probability of B. If A and B are dependent, then the probability that A and B occurs is we still multiply, but we multiply by the probability of B given A has already occurred. Let's look at an example and determine if these events are independent or dependent. Playing the California lottery and the New York lottery are independent events because the result of the California lottery is a totally different state, and that has no effect on the probabilities of the outcomes in the New York lottery. However, the event of having your car start and the event of getting to your statistics class on time are dependent events because the outcome of trying to start your car does affect the probability of getting to statistics class on time. So let's classify the two given events as being either independent or dependent. Finding that your calculator is working and finding that your cell phone is working. These would be classified as independent because they generally don't have anything to do with each other, especially when you're using completely different equipment, like you've got your cell phone in one hand and the calculator in the other. However, I think that we could also change this answer to dependent if we assume that we're using the calculator that is on the cell phone. So you can see where there's multiple ways to answer this question. Here's another example. Finding that your kitchen toaster is not working and finding that your refrigerator is not working. So do these events have anything to do with each other? Well, possibly. I would classify this as dependent because the fact that both kitchen appliances aren't working may be related to each other. Perhaps a fuse has blown in that kitchen area, and so that's causing the appliances to not work. Here's the third example. Drinking or using drugs until your driving ability is impaired, and being involved in a car crash. Can these events impact each other or influence each other? And yes, they can. So we would classify these as being dependent events because having impaired driving increases the probability of a car crash. Here's our first example where we're going to set up and solve for the probability. A new computer owner creates a password consisting of 2 characters. She randomly selects a letter of the alphabet for the first character and a digit, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 for the second character. What is the probability that her password is K9? And would this password be effective as a deterrent against someone trying to gain access to her computer? Reword the probability as an AND probability. So even though we're looking at the probability that her password is K9, here's how we could reword it. We're solving for the probability that she selects the letter K and the number 9 at the same time. It's definitely not an OR situation because we want both of these together. Because this is AND means multiply. So my first probability fraction should correspond to the probability that she selects K. So how many letters in the alphabet are K? Well, only 1. And how many total letters in the alphabet are there? That would be 26. So my first fraction for selecting a K is 1 out of 26. My second fraction corresponds to the probability that she would select the number 9. So how many numbers in the list are the number 9? And that would be just 1. How many numbers total are there in the list? And that would be 10 numbers. So that gives us the probability of selecting 9 as 1 out of 10. Because we want to select both of these together, we multiply them. Now, here's how you would type this in your calculator. When you multiply fractions together, you can multiply straight across. And so we could do 1 times 1 equals 1, and 26 times 10 equals 260. So we have 1 divided by 260, and I did not put the decimal on here, but it's 0.00385. So that is a pretty difficult password to guess, but it's not impossible. And so we know now that the types of passwords that we have to choose are definitely more stringent than just K9. And so we would say this password would be too short to be effective. In the 108th Congress, the Senate consists of 51 Republicans, 48 Democrats, and 1 independent. If a lobbyist for the tobacco industry randomly selects 3 different senators, what is the probability that they are all Republicans? So in this situation, we're selecting 3 different senators, and then we want to know how can they possibly be all Republicans? So let's reword this as an and. We're searching for the probability that we get a Republican and a Republican and a Republican again. So notice that I have 3 different selections listed there, and I have Republican for all of them. Remember, and means to multiply. So I'm going to set up 3 separate fractions and then multiply them together. So let's look at the first fraction in red. It's 51 out of 100. Well, that's easy to determine because there's 51 total Republicans out of 100 total senators. If you add 51 plus 48 plus 1, you get 100. Why is the second fraction different, though? Why isn't the second fraction 51 out of 100 again? Well, notice that my totals changed. And the totals changed because when I picked that first person, I'm assuming they're a Republican because I got 51 out of 100. Well, I wouldn't pick that same person again. And so my total Republicans left to pick from is now 50, and my total senators is now 99. So your totals will continue changing with each selection. So my third selection for Republican again is 49 that are left out of 98 that are left. Now here's how you should type this in your calculator. You don't need any parentheses at all. Start with 51 out of 100 and use your division key and not the fraction key. So type 51 divide by 100 and then immediately type times. Now type 50 divide by 99. Now type times. Then type 49 divide by 98. Now press equals. This is an easy way to enter the whole problem in and to go right to the final decimal. Remember to round it to 3 significant places. So the decimal I see is 0.12878, and so I'm going to round that to 0.129. So the 7 that follows the 8 makes that round up 1 more unit. So would a lobbyist be likely to use random selection? Well, no, because senators would be carefully selected, because not only would they want to get Republicans, but they would also try to get people who would most likely support their cause. It is common for public opinion polls to have a confidence level of 95%, meaning that there is a 0.95 probability that the poll results are accurate within the claimed margins of error. If 6 different organizations conduct independent polls, what is the probability that all 6 of them are accurate within the claimed margins of error? And does the result suggest that with a confidence level of 95%, we can expect that almost all polls will be within the claimed margin of error? Well, when it says that we're looking for the probability that all 6 are accurate, that can be rephrased using the word and. And then the total that you need to include with your probabilities is 6 because we have 6 separate polling places. So the probability, or P, that all 6 are accurate as claimed, I'm going to have 6 different probabilities multiplied together. Now, they tell us that the probability that the individual polling place is accurate is 95%. And that doesn't change for any of the other polling places. So I have the number 0.95 multiplied by itself 6 times. So you can type this in 6 times in your calculator and you'll get the answer of 0.735. Or a shortcut is to use your exponent key. Now your exponent key is a key that's in most calculators to the left of the number 7, and it looks like a little arrow pointing up. So if you type 0.95 and then type that exponent button, this is also a button that's above the x squared key on my calculator. So now you have the exponent key, or the exponent symbol on your calculator, and then type 6 because there's 6 of them. 0.95 to the 6th power is 0.735, or about a 73.5% chance. So, can we expect that almost all polls will be within the claimed margin of error? Well, no, because with several polls, there is a reasonably good chance that at least one of them is not within the claimed margin of error, and we definitely have seen that when we have looked at the poll results that are posted following any type of political election. In a Riverhead, New York case, 9 different crime victims listened to voice recordings of 5 different men. All 9 victims identified the same voice as that of the criminal. If the voice identifications were made by random guesses, find the probability that all 9 victims would select the same person. Does this constitute reasonable doubt? Well, let's rephrase this using an and. Because we have 9 different crime victims, we want to find the probability that all 9 select the same person. So the probability that all 9 selected the same voice, we're going to have 9 different fractions, or 9 different probabilities, all multiplied together. So here's how we would rephrase that. It would be the probability that the first person selected the criminal times the probability that the second selected the same criminal times the probability that the third selected the same criminal, and on and on. Now, this is really a difficult one to understand and to explain to students because it looks so different from the other types of probability setups. Notice that the first fraction represents the first person's pick, and that's 5 out of 5. Now, where did the 5s come from? Well, how many different voices are these crime victims listening to? Well, they're listening to 5 different men's voice recordings, so there's a total of 5 choices. Now, the first person that goes, if we're finding the probability that this is just a guess, well, it doesn't matter who they pick. So they can pick any of the 5 people. So that's why the very first person, their probability is 5 out of 5. Because they can pick any of the different voices that they listen to. Now the ones that follow that, the reason why they all are 1 out of 5 is because we're looking at the probability that all victims select the same person. So all the ones that follow have to select the same voice that the first person selected. And there's only one voice that matches the first person's selection. So that's why we have 1 out of 5, meaning the second person selected the one voice that matched the first person's selection, times 1 out of 5 voices because the third person, there's only one voice that they could have picked that matched what the first person picked, and so on and so on. So if we follow the strategy where we multiply straight across the top and divide that by straight across the bottom, we're going to get a different answer than the one that's posted here. I would actually prefer looking at the decimal instead of the fraction that you see here. So if we do this, we would have 5 divided by 5 times 1 divided by 5 times 1 divided by 5 and keep entering that in until you get all of the different fractions entered in. When I do that, this is the decimal that I get, 0.000000256, meaning that is a very, very, very small probability that all the 9 victims would select the same person if they were randomly guessing. So notice that the first probability is 5 out of 5 because the first person can pick any of the 5 criminals. And the other probabilities represent the event that the other 8 people pick the same person picked by the first person. Now, even though this is proving that this is a very small likelihood to occur by chance, it isn't enough to constitute reasonable doubt, and so that's why the legal team would have to do a lot more to prove their case, but this is probably something that they would like to point out. Here's example 2 on page 163. Consider a sample of 5 pacemakers, including 3 that are good, G, and 2 that are defective, D. A medical researcher wants to randomly select 2 of the pacemakers for further experimentation. Find the probability that the first selected pacemaker is good and the second pacemaker is also good. So first we're going to work this out, and we're going to assume that the 2 random selections are made with replacement. With replacement means that when we select the first pacemaker, we actually put it back before we select the second. So when we put it back, the total will always be 5. Then we're going to work it out where we assume that the 2 random selections are made without replacement. Without replacement means that when we select the first pacemaker, we keep it, and then we select the second. And so when we're not replacing the first, our total for the second selection is no longer 5, but it goes down to 4 pacemakers. So let's try to solve the part A. With replacement means the totals stay the same. So the sample space is we have 3 goods and 2 defectives. So the probability that the first pacemaker is good and the second pacemaker is also good, since we're using and, we multiply. Let's find the probability that one pacemaker is good. So how many goods are there? There's 3. How many total pacemakers are there? There's 5. So we get 3 out of 5 for the first probability that it's good. We multiply by 3 out of 5 again because the totals have not changed, and we're still finding the probability that the second one is good. So 3 times 3 equals 9, 5 times 5 equals 25, 9 divided by 25 equals 0.36. Now let's try part B, without replacement. So now that we got to change the totals when we do the second selection. So the probability that the first pacemaker is good is still 3 out of 5. But the probability that the second pacemaker is good looks very different. Notice that both totals go down because now there's only 2 goods left and there's only 4 total pacemakers left. So we get 3 out of 5 times 2 out of 4, which equals 6 divided by 20, which equals 0.3. There is a rule that we follow in statistics that allows us to get answers a little bit more quickly with estimation. And we can only use this shortcut rule if the calculations are very cumbersome. And so calculations that are very cumbersome, and then when we have a sample size that's no more than 5% of the size of the population total, we can go ahead and assume that the selections are independent even though they may not be. Here's example 3 on page 164. Assume that we have a batch of 100,000 heart pacemakers, including 99,950 that are good, G, and 50 that are defective, D. If 2 of those 100,000 pacemakers are randomly selected without replacement, find the probability that they are both good. So recall that without replacement means that when we do the second selection, we have to change the totals because we're keeping the first one. So first, note that 5% of 100,000, and we're choosing 5% because of that 5% guideline. If we take 5% of 100,000, we're going to multiply 0.05 by the total, and we get 5,000. So even though the sample size of 2 is no more than 5% of the size of the population, we will not use the 5% guideline because this calculation would not really fit the bill of being cumbersome. It's actually quite easy. The probability that the first pacemaker is good and the second one is also good is this. How many pacemakers are good? Well, there's 99,950 out of 100,000 total. Because this is a repeat event, it's like an and so we multiply by the second probability that that one is good. Now notice that both of my totals went down by 1 because this is without replacement. So that means I have to change my totals with the second selection. Now the easiest way to type this one in the calculator is you do 99,950 divided by 100,000 times 99,949 divided by 99,999. Press equals and you'll get 0.999. Now let's try part B. Assume that we still have a batch of 100,000 heart pacemakers. 99,950 are good and 50 are defective. Now if 20 of those 100,000 pacemakers are randomly selected without replacement, find the probability that they are all good. Okay, so let's look at how we would set this up. First, note that the sample size of 20 is no more than 5% of the population of 100,000 as required. Remember, 5% was 5,000. So as long as we're not using any more than 5,000 for our sample, we can use the 5% guideline. But is this calculation cumbersome? Well, let's look at what we would have to do if we set this up by hand. So the probability that all 20 are good, well, that would be, and let's not look at the answers down here, but let's look at the way it would be worked out. It would be 99,950 out of 100,000, and then we would have to change the total each time. We would have to go down 1 from the total for each of those 20 times. And that would result in a very difficult thing to enter in most calculators, and many calculators would run out of space to let you type that whole problem in. And so because this is a cumbersome one to calculate, what we do is we apply the 5% rule. The 5% rule says treat it as an independent event, meaning that we act like we are going to replace the calculators and we don't have to change the totals because there's 20 of them. So what we do is we just take 99,950 out of 100,000 to the 20th power. And so when we type that fraction in, and you do have to put the parentheses around it just like you see on the screen, you get the answer of 0.990. So we are allowed to use this exponent shortcut only when our calculation would be really cumbersome. So if we have a lot of different, a lot of them in our sample, we had 20 compared to just 2 in the first problem, then we would probably want to go ahead and use this rule. A geneticist developed a procedure for increasing the likelihood of female babies. In an initial test, 20 couples used the method, and the results consist of 20 females among 20 babies. Assuming that the gender selection procedure has no effect, find the probability of getting 20 females among 20 babies by chance. Now, anybody who has any experience with having children knows that having 20 females out of 20 babies is not going to really occur by chance. So usually you get about a 50-50 chance of getting a boy or a girl. So when we look at this, we want to be able to determine if the resulting probability gives us strong evidence to support the claim that the procedure is effective. So let's look at how we would set that up. We want to find the probability that all 20 babies are female. and we're assuming that the procedure has no effect. So what's the probability then that you would have a female baby? Well, that's known to be 0.5. So then the probability that all 20 are female can be reworded like this. It's the probability that the first is a female, and the second is a female, and the third is a female, and so on until we get to the 20th is a female. Because we're using the word and, we would multiply all of these probabilities together. And so we would end up with 0.5 times 0.5 times 0.5 20 times. So the shortcut is to use your exponent key, and you would get 0.5 to the 20th power. And again, always round to 3 significant numbers after the zeros. So we get this probability here. This is a very low probability, so we can assume that it wouldn't be likely to get 20 female babies by chance, so that the gender selection procedure would be considered to be effective in increasing the likelihood that babies will be female. And this problem corresponds to example 6 on page 166. Modern aircraft engines are now highly reliable. One design feature contributing to that reliability is the use of redundancy, whereby critical components are duplicated so that if one fails, the other works. For example, single-engine aircraft now have 2 independent electrical systems so that if one fails, the other can continue to work. For the purposes of this example, we will assume that the probability of an electrical system failure is 0.001. Here's our first question. If the engine in an aircraft has one electrical system, what is the probability that it will work? Well, we're told that the probability of failure is 0.001. So the probability that it does not fail, or that it works, is 0.999. And the way you get that number is you subtract the number from 1. So the probability of a working electrical system is equal to the probability that the electrical system does not fail. So we do 1 minus 0.001 and we get 0.999. Here's our next question. If the engine in an aircraft has 2 independent electrical systems, what is the probability that the engine can function with a working electrical system? So the probability that both systems fail would be the probability that the first one fails and the second one fails. So let's find out what that would be. That would be 0.001, that's the probability of failure, times 0.001, that's the probability of the second failure. And we get the number 0.000001. So there is a 0.000001 probability of both systems failing. But that's not really what we wanted to solve for. That we're doing it in a roundabout way. We're asked to find the probability that the engine can function with a working electrical system. So 0.00001 is the probability that both systems fail, so all we have to do is subtract that number from 1. And we get 0.999999. That is a very good probability that the aircraft can function with this electrical system.